Sure. Thank you, Florida. Thank you to the organizers for putting this all together. And everyone can hear me, right? Yeah. So, and thank you as well to Burrard and the other speakers who gave a nice introduction. So I'm going to go right into talking about HERA specifically. So this is what HERA looks like, or will look like. This is, as I said, the Hydrogen Epoch of Reionization Array, which we've heard a bit before, and that's a collaboration of institutions across the United States and in Africa and in Europe, and we're funded by the Gordon Betty Moore Foundation and the National Science Foundation. And this picture of HERA doesn't give you a real sense of the scale. HERA is huge. And that's in part because the 21 centimeter signal is so faint. So we need a lot of collecting area, a lot of sensitivity, but it's going to be made of 350 of these dishes. And we get that sensitivity in part by building out of relatively cheap materials. This thing is made of telephone poles and PVC pipe and chicken wire mesh. But the biggest challenge, as has been sort of discussed throughout this session, is the foreground problem. So we're interested in the 21 centimeter signal from neutron and hydrogen in the early universe. It's coming to our telescope. And in between is all of this stuff, our galaxy and other galaxies that are emitting, for the most part, smooth spectrum foreground synchrotron radiation, which, while it's 4 to 5 orders of magnitude brighter than the signal we're looking for, the 21 centimeter interferometric signal, it is quite spectrally smooth. So any attempt, whether it's foreground subtraction or foreground avoidance, is predicated on the idea that the foregrounds are smooth and you're trying to remove the smooth thing to measure something that is spectrally complicated. But of course, foregrounds and systematics are intimately tied. And part that the reason that won't work is because of calibration. So the thing we measure, this quantity called the visibility, and it depends on both of the antennas involved in the particular measurement. A baseline is what we call that, and it depends in particular on some direction dependent terms, but also here these direction independent gains. It's a complex frequency dependent number. And if these things are not properly accounted for, you can introduce spectral structure that wasn't there in the original measurement and ruin that smoothness, which was the key to separation. Now, HERA is predicated on the idea of using what we call redundant baseline calibration. The idea is that by building a highly redundant array, we're measuring the same pairs of antennas, the same modes on the sky, and therefore the same baselines over and over and over. And so what we're effectively doing is building up a big linear system. So we have 320 in the core antenna gains and 1,500 unique visibilities, but 51,000 total measurements because we're measuring the same number over and over and over. And so what we could do is just basically minimize chi-square. We can write down a model, and we have a model for our unique visibilities and for our gains. We try to solve for those simultaneously, and we want to make sure that that is as close to the data as possible given the noise. And we can actually quantify the degree to which it is a reasonable model or close to the data by writing down a chi-squared per degree of freedom in a sort of standard statistical sense. In the simulations, our code works quite well. We put in something that is purely redundant up to some noise level, and we get back out precisely what we expect, which is that the chi-squared per degree of freedom is 1. In a simulation, the model was perfect. And in practice, this actually is looking pretty good. So here's a bunch of visibilities. These are what we call waterfalls. So it's time on the y-axis and frequency on the x-axis. And all of these are baseline antenna pairs, baselines that are supposed to be measuring the same thing. And quite clearly, they're not. So the process of calibration involves first out throwing away any bad antennas. So antenna 50 never worked. Then we want to actually pose this redundancy constraint, and that lets us solve for all the gains simultaneously. And now they start to look actually quite similar. We want to remove the radio frequency interference, which is a long topic that I could go into it. But basically, you want to flag out the parts where there's bright terrestrial and human-made radio frequency interference. And then finally, we fix to an absolute sky reference. So we only have to solve for a handful of numbers, which is a very different calibration problem than what faces, for example, MWA or LOFAR. So that involves actually doing the sort of traditional radio interferometry where we make a map of the sky. These are not particularly great maps because HERA is not designed as an imaging telescope, but we can make a map of the sky and calibrate it, and our residuals look pretty good to sub 10% levels in terms of our overall calibration. So what this is then, once we have these calibrations, now we can actually compare different days to each other. So the instrument is actually looking quite stable from day to day. And so we can look at one baseline on one particular JD, and we can integrate down and look at it as we sum together 18 different days. And it really just looks like the noise is integrating down and things actually look pretty good. So we're not just interested in the visibilities themselves. We want to start forming power spectra because this is the quantity we want to use to compare to theory. So here's a very preliminary example, but here's sort of what this looks like: is we have sort of some expected noise level, and we have lots of different individual power spectra that are supposed to be measuring the same Fourier mode. And as we start integrating down and integrating down deeper, we're getting, for the most part, modes that are consistent with noise, with some systematic here. And this is with 18 nights of data and just a handful of baselines. Um, and if we then apply a number of techniques, which I'd be happy to talk about in more detail or point you to the papers, where we can actually start identifying that systematic that was living around k of plus or minus 0.5, we're actually able to remove that in a way that is relatively lossless. And so we're getting pretty close to our thermal noise limit on this data, which is about 50 antennas on 18 nights of data. And therefore, we're getting very close to publishing some upper limits. And before we do that, what we really want to do is build confidence that our upper limits actually are, that we actually understand the effects that are going in, and that we can really confidently say that our upper limits mean what they say they mean. So, as an example, and we've looked at many different things, but I wanted to work through one of these, is that HERA is not a simple instrument. And so it will be non-redundant at some level, and our measurements are generally involve combining quantities that we say are supposed to be redundant. So one way to quantify that non-redundancy is actually to look at this chi-squared quantity. You try to make the array as redundant as possible, but you will always fail because it is not quite redundant. And so you can compare statistically the distribution here to what you'd expect theoretically. And we're seeing very strong evidence for slight non-redundancies. Non-redundancy at the sort of 10-ish% level, but clear non-redundancy. Our antennas differ from each other. They're not perfectly placed. They're, the feeds which are suspended at the focus of the dish may not all be in exactly the same place, etc. But we could use this in a number of different ways. One, we can break it down by antenna, and we can actually look for antennas that are strong outliers in this chi-squared quantity. So here, for example, antennas 98 and 136 were particularly strong outliers across the spectrum in this chi-squared broken down by antenna. And so we use that actually to pick out the antennas that we felt were the most redundant with each other. We picked out we threw out the outliers and kept the median distribution. And so the one result of that is now we can actually go and calculate to what extent is this the fact that we're measuring the same thing over and over, but we're not actually. What kind of decoherence is that creating? Because if you're combining quantities that are supposed to be the same but aren't quite the same, they will average down a little bit, and that will lose signal. And what we're seeing in our metric for decoherence is something like a 5-ish% decoherence. And so this is all going into a preliminary, power spectrum measurement, which I can't show you the actual numbers on quite yet because we're not done checking all the boxes. We've already published these papers on redundant calibration, absolute calibration, reflection, and crosstalk systematics, and now we're preparing a final sort of push, a suite of papers on how we're estimating our error bars, how we are our upper limits themselves, our validation of the pipeline on entirely simulated data, and then how we're interpreting that cosmologically. So look forward for that later this year. Now, in addition to those 18 days, we've also got over 100 days in the can from HERA phase 1. And meanwhile, that instrument is in some sense gone. We kept the dishes, but the entire digital system and the feeds are completely replaced. In particular, we're replacing them with these broadband Vivaldi feeds that let us go out to Redshift 29. Although perhaps we won't make a measurement out to 29. And that will actually be once we get down, from about 50 antennas to about the 300 that we're designed to do, we will have way more sensitivity to basically any cosmological signal, not just at EOR redshifts, but also these epoch of X-ray heating cosmic dawn redshifts. And if, for example, the edges detection is correct, that should also raise up the amplitude of the signal around redshift 17 interferometrically, which we should be able to see. But in the EOR, which I think is the interest of a lot of folks here, this should let us really precisely constrain the ionization history of the universe. So with the sort of fiducial HERA measurement, we should be able to really knock out this question of how did reionization proceed. We're also, as we're sort of getting this new instrument ready, we're using these quantities like chi-squared as a real-time diagnostic. So we built out this redundant calibration into our real-time system so that we can understand within a day which antennas are working and why are things going wrong. And you look at all of this and you wonder, what is all of this? Some of this is radio frequency interference. Some of this I'm not sure yet. Some of this is effects of the sky, but it's a lot of things that we have to go through and sort of use this to diagnose how our system is operating. So to sum up, I've said that HERA is a purpose-built 21 centimeter experiment. It's really designed to do this one thing. And we have, from the get-go, this robust calibration and systematics control and redundant calibration is all part of the design. And we're now building out to a very, very large array. This thing will be as big as Arecibo was. And we're putting now the finishing touches on this suite of papers supporting our first upper limits, which should be deep enough to actually say something about the physics of the IGM at that time. Though it'll be ruling out models that probably nobody believed in anyway, but that's the place you have to start. And in time, we should be able to follow up edges and also very precisely constrain the epoch of reionization with the power spectra coming out of the full HERA system, which we hope to see in the next couple of years. So with that, thank you so much.